Okay, so the module for week 2 is a review of sequences and series. You'll need the series information in particular for the next 2 weeks on convergence and divergence. So normal setting, we would do a review and then we would have in new information on non-arithmetic, non-geometric patterns. But we'll be skipping that part for this year. But again, to assure you, Ms. Cohen says it's all good. You'll still be good for calculus. So some review. A sequence is just any ordered list of numbers. So a sequence can be arithmetic or geometric, but an ordered list of numbers doesn't have to be an arithmetic sequence or a geometric sequence. So you can call it a sequence if it's any ordered list of numbers. It's also a function whose domain is the set of positive integers. I'm going to put C there. C, remember, is the symbol for integers. So basically, the domain is the terms that you have. So you'd have a first term, a second term, a third term, etc. That's why it is the positive integers. Individual numbers are called terms. And we separate the terms with commas in a sequence. Just some notation. So a series is just the sum of a sequence. Again, the particular list of numbers doesn't have to fall into any specific type of pattern, but you have this ordered list of numbers, and if you want to add up that ordered list of numbers, it's now called a sequence. A sequence can be finite, meaning it has a final number. That's called the nth partial sum. Or it can be infinite, meaning it goes on forever. So most infinite series, most, not all, cannot be summed. And we take our terms and we separate them by plus signs because we're one added terms instead of just list them. So if you take your ordered list of numbers and it is a particular type of pattern, then it could be an arithmetic sequence. So an arithmetic sequence is a sequence whose pattern is created by adding a constant to generate the next term. And this constant is called the common difference. Designated by a D. Arithmetic series are an example of a linear function because we have a constant increase or a constant decrease, just like a slope. A geometric pattern would be a sequence whose pattern is created by multiplying, not instead of adding, multiplying a constant to generate the next term. And we call that constant the common ratio, designated with an R. And you'll find that a geometric pattern is designated by an exponential function. It's also important with a geometric pattern that the common ratio is what you are multiplying each time, not what you're dividing by each time. So if you can think of it in terms of something you're dividing by, then it's the same as multiplying by that reciprocal. And the common ratio has to be what it is that you would multiply by. It cannot be what you would divide by. So I went ahead and did this bottom part. So if we were to graph, elections for U.S. president have been held every 4 years since 1792. Graph the arithmetic pattern on the set of coordinate axes. So when you graph a sequence, your x-axis is n and your y-axis is a sub n. So your x-axis would always be positive integers because it represents a first term, a second term, a third term, a fourth term, etc. Whereas your y-axis is the actual value of each term, so that could be anything. So the first term would be the first election in 1792. The second term would be the next election, which is 4 years after. And then every subsequent election was 4 more years later. So there is a constant addition of 4 years, which creates that linear pattern, which is an example of an arithmetic sequence. Say you're offered a salary of $40,000 for your first year with a guaranteed raise each year of 5%. That is an example of a geometric pattern. Again, your x-axis will be n, which is just which term are we talking about, which will be positive integers, and an a sub n could be anything. It's the actual value of each term. So if the first year you make $40,000, your first point would be 1 comma 40,000. 40,000 adding 5%, second year is 42,000. So that would be your second point, 2 comma 42,000. The second term or the second year is 42,000. Add 5% to that. Now we're up to 44,100, and that would be your third year or the third term, and another 5% to that brings us up to $46,305. And so you can see that it is growing exponentially here, and that would be the case with any geometric pattern. So some of the formulas that you needed in advanced algebra. Our arithmetic sequence formula, a sub n equals a sub 1 plus n minus 1 times the common difference. So a sub 1 is always the first term. N is the number of the term that we're looking at. Again, that's going to be a positive integer. D, the common difference. What are you adding from one term to the next? Or if D is negative, you would be subtracting. A sub n and n, obviously there's got to be a relationship. They both use n, except that this is which term you're talking about, and this is the value of that term. So if n is 4, we would like to know what number sits in the fourth term's spot. So rarely will n and a sub n be the same value. The only way that would occur is if, say, the 7th term is 7, or the 11th term is 11. So it can happen, but it's rare. These are positive integers. These can be any value because it's just what value is sitting in that particular position. Our geometric sequence formula, we have sort of the same thing, except instead of D, we use R. A sub n equals a sub 1 times R to the n minus 1. Remember, this is linear and this is exponential, and you can see the formula involves an exponent. So Again, a sub 1 is the first term. R is what you are multiplying each time to get from one term to the next. N is which term we are talking about, positive integer, and a sub n is the value of the term that we're talking about. So let's kind of work our way through a couple practice problems. So first, we're going to find the nth term or the general rule for each of the following arithmetic sequences. So basically, you're going to use the formula right here and substitute in what you know. We can see from this pattern that the common difference is -2 because each time we're taking 2 away to get to the next term. So to write the nth term or the general rule, we use a sub n plus equals a sub 1 plus n minus 1 times the common difference. Even though the formula never has a parentheses around d, I would get used to doing that because when d is negative, then it can be mistaken for subtraction instead of multiplication. So to find the nth term and general rule, we're going to substitute in the first term, and we are going to substitute in the common difference. And then when you clean that up, so you would distribute right here. So you have -2n plus 2, and then you can combine your like terms. So your general rule is a sub n equals -2n plus 12. Okay, which is just this simplified. So that means that now that I see this, if I plug 1 in, I should get 10 because the first term was 10. If I plug 2 in, I should get 8. If I plug 3 in, I should get 6. So you can test your general rule out. But then you could use this to say, find the 5 millionth term or the 222nd term or the 11th term, whichever term you want. You just replace that number with n, and that should tell you the value of that term. So for number 2, you can always find the common difference if it's not obvious to you by taking any term and subtracting the one in front of it. So again, if it's not obvious what it is that you're adding or subtracting each time to get to the next term, try that. Any term minus the one in front of it. And you could pick that from anywhere. So I could do -7/2 minus -1 or -1 minus 3/2 or 3/2 minus 4. It's completely up to you. In this case, the common difference is -5/2. Okay, so following what we did in number 1, we're going to do a sub n equals the value of the first term plus the quantity n minus 1 times that common difference. Okay, so you're going to clean that up. You want to distribute the -5/2 and combine them like terms. And what you're going to end up with is a sub n equals -5/2 n plus 13/2. So if you want to test out that general rule, if you substitute in 1, you should get 4. If you substitute in 2, you should get 3/2. Substitute in 3, you should get -1, etc. And then you can use that general rule, substitute any integer, positive integer in for n to find out the value of any term. Okay, so we have a little more work to do in number 3 because they gave us the first term, but then just the 12th term. So I need to know what the common difference is because so far all I've had to substitute into the formula is the first term and the common difference. And I've got the first term, but I got to figure out the common difference. So basically you can do an average to find the common difference. You can do the 12th term minus the first term. So the value of the 12th term minus the value of the first term over the 12th term minus the first term, and that's sort of find the average. You get 44 over 11, and now we know that D is 4. You could also substitute in, like you could do, you could use this formula up here, and you could say 46 equals 2 plus 12 minus 1, because the 12th term is 46. So you could use this as 46 and this as 12. So the 12th term is 46. We know the first term, and you could solve for D as well. So now we're going to do a sub n. We know the first term is 2 times the quantity n minus 1, and we figured out that D is 4. And when we clean that up, we left with 4n minus 2 as our general rule. So let's try that again. Over here, let's find the common difference. So if we do it as just a ratio, we can do 85 minus 94 over 6 minus 3. Or you could use the formula, but this is going to be faster. You get negative 9 over 3, so the common difference is negative 3. We're going to use the formula, and we're going to substitute a sub 1. Well, we need to know what a sub 1 is. So you can figure that out either using the formula or just some quick thinking. If the third term is 94 and you're decreasing by negative 3 each time, then the second term must be 97 and the first term must be 100. Again, you can also use the formula to find that out. So I've taken the formula, I figured out that the first term is 100 based on the third term being 94 and the sequence decreasing by 3 each time, and my common difference is negative 3. And when you clean that up, you have a sub n equals negative 3n plus 103. And that is your general rule. Okay, so moving on to a general rule for geometric sequences. So for arithmetic, you can find the common difference by taking any term and subtracting the one in front of it. For geometric sequences, you can find the common ratio by taking any term and dividing the one in front of it. We're going to use our sequence formula. A sub n equals a sub 1 times r to the n minus 1. And just like we did before, we're going to leave the a sub n and the n because it's a general rule. We want to be able to substitute any n value in to find any term's value. So we're going to replace a sub 1 with the 5 and the r with the 3 halves. And then that's it. You cannot actually simplify that anymore because order of operations would tell you that you need to take care of the exponent before you can multiply. So you cannot put these two together in any way. You need to be able to substitute some n value in first, then do the exponent, and then multiply. So that's your general rule. There's not a lot to do after that. All right, so here they didn't tell me what my r value is. They did, in fact, tell me a sub 1, so that's good. So I can get that started. I've got a sub 1, but I need to know what r is. So once again, r is any term divided by the previous term. It doesn't matter which term you divide by which previous term. So if I did say 4 divided by negative 6, that's negative 2/3. But negative 6 divided by 9 is also negative 2/3. So it doesn't matter. It's also how you can verify it. You could just do it a couple times, make sure it matched. So we just plug in for a sub 1 and r, and that's our general rule. Once again, you cannot simplify that anymore. Okay? You cannot multiply the 9 times the negative 2/3 because you would have to follow order of operations and take care of the exponent before you could do that multiplication. Now, number 7's got a little extra there. So we need to find the value of a sub 1 and the value of r here. The problem for geometric is it's not linear, so we can't just set up a ratio like we did to find the common difference. So if you were to kind of set up what this sequence looks like, there's some unknown first term. We know the second term. We don't know the third or the fourth, but we do in fact know the fifth. So what you can do to find both a sub 1 and r here, once you set that up, you can use the formula, but basically you're going to use the complete section that you know. So from a start that you know to an end that you know, and just pretend that that is the complete sequence in order to find what you need to know. So I'm going to just use this portion. And if I use that portion, then I'm going to use 2/3 as my last term. I'm going to use negative 18 as my first term. I'm trying to find r. And if negative 18 is first and 2/3 is last, then that would be 4 terms. And then I should be able to solve this equation to find r. So I can divide both sides by negative 18 or multiply times negative 1 over 18. I get negative 1 over 27 equals r cubed. And then when you take the cube root of both sides, the cube root of negative 1 over 27 is negative 1/3. So now I know what R is, and if I know what R is, I could fill in any of these blanks. To go forward into the sequence, you would multiply by negative 1/3. So to go backwards, you would divide by negative 1/3 or multiply by the reciprocal. And that would tell you that this would have to be 54. 54 times negative 1/3 is what would give you negative 18. Then I can write my general rule. A sub 1 equals A sub n equals a sub 1 times r to the n minus 1. So this is my general rule now that I found what a sub 1 and r is. So now that we've reviewed sequences, let's talk about series. So we have the same information, but now we're trying to add up all the terms. So we should expect bigger answers, or I guess even smaller answers, depending on if the sequence increases or decreases. So it's the same list of numbers, but separated with a plus sign instead of a comma. We call these partial sums because they're not going on forever. Okay, that's all that means, is that there is a stopping point. We want to add the series, say, from the first term to the 10th term, or from the first term to the 100th term, but it doesn't go on forever. There is a final point that we want to stop and add up our terms, and that makes it partial because it doesn't go on forever. Okay, so we can see that the formulas use the same information that we had before. Instead of a sub n, it's s. S just means the sum. So if n, remember a positive integer, let's say that we want to find the sum of the first 10 terms. So n would be 10, and we'd find s sub 10, the sum of the first 10 terms. A sub 1 would be the value of the first term, and a sub n would be the value of whatever this term is. So if n is 10, this would be the value of the 10th term, and this would be the sum of the first 10 terms. Then over here, again, exponential. So it's got some exponents involved. We need the first term, we need the common ratio, and we didn't need to know to what term do we want to sum the series, and this is equal to the sum of that series. Okay, so find the following finite sums. The first 50 terms of the following, it's a series because we don't have commas anymore. We have pluses and minuses. So it goes from -6 to -2 to +2 to +6. So we can determine that this is arithmetic because we can see it's going up by 4 each time. Again, if you're unsure, take any term and subtract the previous term. So 6 minus 2 is 4. 2 minus -2 is 4. -2 minus -6 is 4. So you can determine that there's a common difference of 4, and a common difference tells you that it's an arithmetic pattern. We can see that we have a first term of -6. If we want to find the sum of the first 50 terms, though, then we need to know what the 50th term is. So right now, we know the first, second, third, and fourth, and we know what we're adding each time, but we don't know what the 50th term is. But for this formula, we need to know that. So if we need a piece of information for our series formula that's not given, then we're going to have to use the sequence formula to find it. Otherwise, you just have to write out this whole series until you get to the 50th term. And we all have more time on our hands right now than we'd like to, but I don't think any of us wants to write out the first 50 numbers here. So I'm going to start with the sequence formula. And I'm trying to find the 50th term. I know the first term. I know that n is 50. And the common difference is 4. So I have enough information to use my sequence formula to find the 50th term. And when you do that, you get that the 50th term is 190. 49 times 4 minus 6. Once I have that, then I can use that with the series formula. S sub 50 equals 50 divided by 2, the first term, plus the 50th term. Okay, I want the sum of the first 50 terms. This is the first term. This is the 50th term. And there would tell me that the sum of the first 50 terms of this pattern is 4,600. Okay, for number 2, it tells us it's geometric. It gives us a sub 1 and it gives us r. And it also says to find the sum of the first 10 terms, which is telling us what n is. So if you look at this formula, I need to know the first term. They gave it to me. I need to know r. They gave it to me. And I need to know what n is. In other words, how many terms do I want to add together to get this sum? And they said 10. So they've given me everything I need for this formula. I want to find the sum of the first 10 terms. If the first term is 8, r is 1/3. I'm trying to find the sum of the first 10 terms, and that's divided by 1 minus r. Just be really careful when you're putting this in the calculator. Just make sure you mind your notation, because sometimes, that can make the difference between getting the right answer and the wrong answer, even though you have everything plugged in correctly. So if you put this in the calculator, you get 11.9998. We're going to round that to 12. So it doesn't equal exactly 12, but it's pretty close. Okay, next example. So we can see that it's arithmetic because it looks like we are adding 5 each time. So we're going back to this formula. So we know that the first term is 2. We know that the last term is 62. But we don't know how many terms there are. This ... we're not sure. So again, if you have the time, if you want to just sit there and keep adding 5 until you get to 62 and then count them up, you could do that. Or we could use the formula that we learned before, which is sequences. So right now we know a sub 1 is 2. We can see that the common difference is 5. And we can see that a sub n, the last term, is 62. We just don't know which number term 62 is. Is it the 10th term? Is it the 20th term? What is it? So we're going to use this sequence formula. We know that a sub n, the last term, is 62. We know the first term is 2. We're trying to figure out which term 62 is. We know the common difference is 5. So using that formula, you can solve that and find that n equals 13. And now we have all the information we need for our formula. So we're going to find the sum of the first 13 terms. N is 13. The first term is 2. The last term is 62. And the sum of those first 13 terms is 416. Number 4. So we would assume, you could probably assume that this is geometric, just given that it has 2 to the 12th power over here. But remember, if you aren't sure, you can take any term and divide by the previous term. And if you get a common ratio, so like 4/3 divided by 2/3 and 2/3 divided by 1/3, if you continue to get the same value when you do that, it's a common ratio. If you wanted to see if it was arithmetic, it would be 4/3 minus 2/3 and 2/3 minus 1/3, and you would not get the same result each time there. So let's see. We've got a sub n equals first term. The common ratio is 2. You're multiplying by 2 each time. So that is our general rule. And so we can figure out then what term this is. Here's the things we need for our series formula. We need to know the first term, we need to know the common ratio, and we need to know n. So again, we need to know like how many terms, if we had all the terms written out, what place does this hold? Is it at the 10th term? Who knows? So you can solve this equation to figure it out, or you can kind of look at the patterns. If you plug 1 in, you get 1/3. If you plug 2 in, you get 2/3. And you can kind of look at this exponent here and determine that this would in fact be the 13th term. Or you can substitute this value for a sub n and solve for n. So we want the sum of the first 13 terms, a sub 1 times 1 minus r to the nth power over 1 minus r. And the sum of the first 13 terms, you should get 2,730 and 1/3, or 0.3 repeating. Okay, the next topic for review is sigma notation. Feedback I get in magnetometric algebra is students are just not real big fans of sigma notation. Sigma is just a letter from the Greek alphabet, but it's also called summation notation. So you hear both of them. When you see the symbol, this is sigma notation because that's sigma, the letter from the Greek alphabet, but then summation notation because whenever you see that, it means you're working with a series and you're trying to find a sum. Okay, so depending on what type of expression is right next to the sigma notation, it could be any type of pattern. It can be arithmetic if this is linear. It can be geometric if this is exponential, but it can be some other pattern depending on what this expression represents. If it's linear or exponential, it's arithmetic or geometric. If it's some other type of expression written here that is not linear or exponential, then it's some other pattern that is not arithmetic or geometric. Basically, what you do here is you've got, this is the expression, the rule that generates the terms. The number down here, which isn't always 1, could be something else. If you plug this number, substitute it in for n into your expression, you've generated the first term. And the top number generates the last term when you substitute in. And to get all the terms, you just start with the bottom number and you go in order, because remember n is positive integers, you just go in order until you get to the top number, and that generates your whole list. And because it is summation notation, we would want the sum, so we would add those together. So there is a function in your calculator. If you've got a fairly updated calculator, it doesn't have to be the newest, but if you hit alpha window, number 2 will say summation, and then you'll see that little sigma. And so alpha 2 would give you the place in your calculator where you could have the calculator help you figure out the sum of that sigma notation. But let's try and do this one by hand. The fact that n plus 3 is linear would tell us this is arithmetic, and that's just important so we know which formula we want to use. We don't really want to do this all by hand, as in generating this whole list of numbers, is because we're going from 1 to 500. That would be a lot of terms, and you don't want to do that. So it'd be nice if we had a formula. So the fact that n plus 3 is linear, again, means that we would use our arithmetic formulas, okay? Because this right here is linear. So n is always equal to the top number minus the bottom number plus 1. So in this case, 500 minus 1 is 499, plus 1 is 500. If the bottom number is 1, then n will equal the top number. But the bottom number doesn't always equal 1. And so you can't always just say n is the top number. And if you subtract, you need to add back that 1 to get the correct n. So in this case, n is equal to 500. Now, it will always be the top number if the bottom number is 1, just not always that. So let's see, I need the first term. Remember, here's our formula. I need to know what n is. I need to know the first term and the last term. So the first term is what you get when you substitute in the bottom number. So a sub 1, I would substitute 1 in for n, and I would get 4. If you substitute in the top number, you get a sub n. So a sub n would be 500 plus 3, or 5 over 503. So now I can use my arithmetic series formula. I know that n is 500. I've generated the first term by plugging in the bottom number. I generated the last term by plugging in the top number. Now I have everything that I need for my formula, and the sum of the first 500 numbers is 126,750. Okay, you can try that in your calculator too. Again, it's alpha window and it's option 2. So if we go through these other examples, this is arithmetic because this is linear. This one would not be arithmetic or geometric, so we don't really have a formula to use. This is geometric because it's got an exponent, and this is geometric because it's got an exponent. So being able to look at and determine if it's arithmetic or geometric just gives you some formulas that you can use. So for number 2, 2n plus 5 is linear. I do want to use a formula because I'd have to go from the 11th term to the 30th term, and that's more than I want to have to write out by hand. So let's see. For the arithmetic series formula, I need n, top number minus bottom number plus 1 tells me that n is 20. There's 20 terms if you start by plugging in 11 and you stop when you get to 30. A sub 1 is what you get when you plug in the bottom number, which is 11. 22 plus 11 is 27. A sub n is what you get when you plug in the top number, which is 30. So you get 65. So S sub 20 is 20 over 2 times the quantity 27 plus 65. And we get the sum of those first 20 terms, or the 20 terms from the 11th to the 30th is what we're finding is 920. So again, for number 3, because this is quadratic, so that's neither arithmetic nor geometric. The good news is I'm only going to go from 0 to 5. So I don't really need a formula. That's not that many terms. So the first term is what you get when you plug in 0. So if I started plugging in 0, I get 1. Then I'm going to plug in 1 because I started with 0. So the next is plug in 1. If I plug in 1, I get 2. Then I'm going to substitute in 2. So 2 squared plus 1 is 5. Then I'm going to substitute in 3. 3 squared plus 1 is 10. Then I'm going to substitute in 4. 4 squared plus 1 is 17. And I'm going to stop with 5 squared plus 1, which is 26. So there are 6 terms in this pattern. Okay, start plugging in 0, then plug in 1, substitute 2, substitute 3, substitute 4, stop when you get to 5. This is the entire series, and then if you add them all up, the sum of those 6 terms is 61. But there's no formula to use. You have to just generate the whole series and then add them up. For numbers 4 and 5, we have an exponent there, so we know that they are geometric. Basically, this right here is going to fall into the pattern a sub 1 times r to the n. So that's going to tell us what a sub 1 and r is. And then we already talked about previously that n is the top number minus the bottom number plus 1. So the geometric series formula, there's 11 terms that we're summing, and we need a sub 1. A sub 1 is going to be that coefficient up here. So a sub 1 is 2. R is going to be the base to the exponent. N we already determined is 11. And then 1 minus R. We already talked about that. So we have everything we need for our formula. If you're unsure, like you're like, oh, so I don't really know, just because you're telling me that 2 is a sub 1 and 3 is r. Well, generate a couple terms. If you substitute in 0, remember anything in the 0 power is 1. So if you put in 0, the first term is 2. If you put in 1 for n, the second term is 6. If you put in 2, then the second term is 18. And you can, if you list out a couple consecutive terms, then you can verify that the common ratio is 3. So that can go in your calculator, and the sum of the first 11 terms here is 177,146. So we said that number 5 is also geometric because, again, there's an exponent. And so we need to know n, a sub 1, and r. So based on this being geometric, I can say that a sub 1 is 4 and r is 9/10. N would be the top number minus the bottom number plus 1, which gives you 9. So if you start by substituting in 0 and you stop when you get to 8, there'd be 9 terms altogether. So we've got that it's geometric, so we know we have a formula that we can use. If you substitute in 0, that would give you the first term, and it is 4. And if you generate a couple consecutive terms, you'll see that the common ratio is 0.9 each time, but the coefficient will always be a sub 1, and the base to the exponent should also be r. So we have everything we need for our formula. And in your calculator, you get about 24.503. But then if you hit math enter, it gives you this awful fraction. But that would be the exact number. So you have an exact answer right there. All right, the last bit to review. Under what conditions can an infinite series be summed? Well, it has to be a geometric series. The absolute value of r has to be less than 1. And third, there are a few other types of infinite series. But we will talk about that one later. So for now, because we've only talked about arithmetic and geometric, for an infinite series to be summed, it has to be geometric, and the absolute value of the common ratio has to be less than 1. Okay, we have a special formula for an infinite geometric series. It's the simplest of all the formulas. So remember, the capital S means sum. If it's an infinite series, then we don't put a subscript. Sometimes you might see a little infinity here, but if you don't see the subscript, then it's infinite. And we need the first term in the common ratio. So right here, this is the same thing as 3 times 1/2 to the nth power. Okay, that's the exact same information. You could also generate a first couple terms. Like if you plug in 0, that's your first term. And so you get 3. And then if you plug in 1, you'll get 3/2. And you can plug in 2. And when you do that, what you'll see is that your common ratio is 1/2. Well, the absolute value of 1/2 is less than 1. So that means we can go ahead and use this formula. So the sum of this infinite series, if we rewrite it like this, remember we talked about before, 3 is a sub 1, but you can also plug 0 in to generate that. And then we determined that r was 1/2. And so the sum of our infinite series is 6. To kind of visualize how an infinite geometric series works, take like a piece of paper, and if you cut it in half, get rid of one of the halves. So we're just going to use half of the original sheet of paper, and we're going to keep that pattern. So we're going to keep taking the half that we still have and cutting it in half, and taking half of that and cutting it half again. So we're just going to keep taking these halves and halving those. So eventually this piece of paper is going to get to be so small that you can't physically cut it in half anymore, but that doesn't mean that it still doesn't exist and that it's technically, theoretically still possible to half it. And so it just starts to approach where this piece of paper gets to be so tiny that we kind of throw up our hands, but it can actually theoretically still be halved. And so it approaches some that, that we consider to be finite, even though we could theoretically keep taking half. For this one, so based on this being a sub 1 times r to the n, a sub 1 would be 1, because if you put in 0, anything to 0 power is 1, and r is 7/6. Well, the absolute value of 7/6 is greater than or equal to 1, and so we do not use the formula. We just say there is no sum. You want to make sure that you check that, though, because you can substitute the information into the formula and get an answer. It just won't be right. So there is some practice problems posted in your folder, and the answers are provided. And then you have the assignment that will be due by the end of the week.